All right, so I had to make a quick step there. The iPad was acting up. So, all right, so this actually can be found. This definition can be found by applying the change of base logarithm formula. So, if you guys remember from algebra, there was a change of base formula that said you can change this to any base you want. And what happens here is that you have log base b of x over log base b of a, right? So you change it as long as those two are matching. You guys know where that comes from, and you know that this is your old base, right? So what we're saying here is that if you change this to log base e, well, we know that log base e is the natural log. And so, but in this case, a is an actual number, right? Is a real number. And so what we have here is that this is 1 over natural log of a times natural log of x. So this is just a real number times a natural log of x. So that's where that's coming from, right? All right, let's review a few logarithm uh, um, properties from algebra. Remember that logarithm base a of 1 is 0. The logarithm of product rule is that the log base a of x times y will be the logarithm base a of x plus the logarithm of a of y. Then we have also the power rule, logarithm base a of x to the n. The power becomes a factor of the logarithm. And then we have the quotient, logarithm base a of x to the x over y becomes log base a of x minus log base a of y. So those are a few of those properties that we have discussed before. From the definitions of the exponential and logarithm functions to the base a, it follows that f of x equals a to the x, and the logarithm g of x equals log base a of x are inverse functions of each other, right? Just like before, we can argue that those two are inverse of each other. So therefore, whenever we have a to the x, it's going to be true if and only if x equals log base a of y, meaning that you interchange the x and the y's. In other words, that if you input a logarithm in the exponential, remember that this is the input of an exponential, and then this is the input of a logarithm. So whenever you input a logarithm in the exponential, what's going to happen? They're going to undo each other. Now they have to be matching the bases, right? So they're going to do each other, giving you back x. Or if you input the exponential into the logarithm, and they both have the same base, right? Then they undo each other, and then you get back x. All right, so that's how the game is played, right? You know now how to undo some any logarithm. Now we have such we have a special logarithm called the common logarithm function, and that is an exponential with base 10, and it is known to be common logarithm because it was the most common used logarithm for the longest time. Um, if you guys notice, this one had a lot of times you will notice that the logarithm for base 10 is never actually is never specified that it is base 10. It's missing, right? When it's missing the base, it is assumed that it is going to be a base 10, right? If you guys notice in your calculator, that's sort of what you will see. In fact, you will see the log button, and then you're gonna see on top of it, you're gonna see 10 to the x, and that's not a mistake, right? They put those together because those two are inverse of each other. Just like if you guys notice on your calculator, ln and e to the x, these are inverse of each other, right? But they're both same base. Okay. All right. So now we're gonna go ahead and use example 2 to solve some of these equations and use some of these properties. So let's solve the first one. We have 3 to the x equals 1 over 81. we can use here what we call the one-to-one function, one-to-one property. And that means that we compare to the left side and the right side one by one, we should be able to sort of create an equation from it. So what I did here is I rewrote 81 in the form of an exponential base 3. That way, because at some point I want to make sure that those two are equal to each other or look the same. And then I move this to the top. And when I move that to the top, the base kind of changed sign. So now we can say compare the bases with the base, and then therefore the exponents must be the same. So x equals -4. This is done by the one-to-one property. Let's try the next one. We have log base 2 of x equals to -4. Now, for me to remove this logarithm so I can get to the x, I need to remove this logarithm. Well, I know that the exponential base 2 will undo the logarithm base 2. So what I'm going to do is I'm going to erase these two to be powers of a base 2, right? So this is 2 to the power of logarithm base 2 of x equals to 2 to the power of -4. Since these two are the same, that means that these two are the same, right? Because the base are the same, the powers are the same. But by doing this, remember that these will undo each other. So therefore that will give us x. This will give us 2 to -4, which is 1 over 2 to the 4. Now this looks like a 24, so let me rewrite that. There you go. And that's 2 to the 4, which is 16, 1 over 16. All right. So let's get to the nitty gritty. So what we want to define here is the differentiation and the integration of this of these exponential bases other than e. So it's actually going to be very similar to e, and that's the reason why we sort of connected to relate them back to the natural logarithm. But if you guys remember that the logarithm, the derivative of e to the x is e to the x, right? It's itself, right? So if you think about it, if we try to mimic that sort of approach, we can sort of kind of come up with these rules by doing that. So let's go ahead and do that first one. So we had a to the x, and we're trying to do the derivative of this. So if we do that real quick, we can rewrite this as e to the x times natural log of a. And we're going to do the derivative, right? Remember we did that in the beginning. If we check the derivative of this, what's the derivative of this? Well, itself, right? It's itself times the derivative of the power, which is going to be, what's the derivative of x times natural log of a? Natural log of a. Now, what is this right here? Well, we can move that back over here, and that will give us back to not the a to the x, right? So we get back to that. So what we're saying here is it's sort of kind of like the same thing as the e to the x, where it's the same thing, right? Itself is the derivative, but we just gotta multiply the front by the natural log of a. That's all we're saying. Now remember that in this one, in the logarithm, when you took the logarithm of 1 over the derivative of natural log of x, it was 1 over x, and sort of this became a denominator. Well, instead of you multiplying by natural log of a, that sort of kind of becomes a denominator, right? So it kind of is consistent with, well, this will turn into a denominator, so that will turn also to a denominator. So that's how I like to remember it. We can generate this rule again, just like we did it up here, but you guys can try that on your own if you want to. Now we do have to be careful when we are dealing with the function instead of function. So when you do the derivative of this, it will be itself multiplied by natural log of a, right? That's because it is special exponential other than e. But at the end, you gotta multiply it by the derivative of the inside, right? So you have to do, you have to make sure to remember to multiply by natural log of a. And over here is the same idea. It will be 1 over u multiplied by natural log of a, but don't forget to multiply the whole thing by the derivative of the inside. All right, so example 3 will give us a chance to practice this conditions here. So the derivative of 2 to the x, it will be 2 to the x times natural log of 2. All right. What about this one? The derivative of 2 to the 3x, it will be itself multiplied by natural log of 2. And then don't forget to multiply by the derivative of the inside, which will be 3. And then you can multiply that to the front. For logarithm, we'll do the same thing, right? This is the inside of the logarithm right here, the cosine of x. So we'll do derivative of that will be 1 over the inside. Don't multiply by natural log of the base 10, and then don't forget to multiply by the derivative of the inside, and that will be negative sine of x all over natural log of 10 times cosine of x. Now remember that this can simplify to be a tangent of x. We carry the negative, so that gives us negative tangent of x over natural log of 10. Over here, this is going to be a little more special, so I'm going to zoom in here real quick. So what we did here is a little bit something more more efficient, right? Instead of doing the derivative of this logarithm with this quotient, I chose to separate this into 2 different logs. This actually, you guys will see how this is going to be more efficient. Now, if you try to think about what the derivative that you will have to do here is, you have to bring this to the denominator and then multiply it by the derivative of this, and then so it just gets pretty messy, right? So if you separate like this, then this is going to allow you to be able to take the derivative much easier. So I'm using the quotient rule of logarithms to separate them, and so thus we have the derivative of this one will be 1 over its inside. That's that, multiplied by the natural log of its base. And then don't forget to multiply by the derivative of the inside. And then minus, because of the quotient here of the log. And then we have 1 over its inside, multiplied by the natural log of the base, times the derivative of the inside. And then this will simplify to be, the derivative of this will be 1/2 x to the negative 1/2. So that will give us that. The derivative of this is 1. This 1/2 will simplify to be 1 over 2. And these will simplify to be x on the bottom minus that. And then you can have common denominator by multiplying this by x plus 5 and multiplying this by 2x. And then simplify that, and that gives us 5 minus x over that. Missing here that. Okay. All right. So mainly the last part was just algebra. All right. So lastly, we're gonna discuss the integral of the exponential function, and it sort of follows the same condition as before. So it would be the integral of this of an exponential will be basically itself, right? Itself, just like e to the x is itself, except that we're gonna have to divide by the natural log of a, divide by the natural log of its base, and then so that will give us the antiderivative of it, right? So real quick here, so we're gonna do the integral, the antiderivative of this one right here. So it's almost, it can almost follows, right? Because the antiderivative of this, it will be itself divided by the natural log of its base. So that's it, right? It's just remembering the formula and be able to set it up. So just pretty much is the antiderivative itself just divided by the natural log of its base. So theorem 5.14 wants to extend this or sort of generalize these properties, right? We just because we already have a lot of these rules, the power rule for exponents, we can sort of generalize it for using the exponential. So we'll see that some kind of going on in here. All right, so but we want to make sure we clear up how we apply these rules, and we want to remind you some of these some distinctions about some of the setups of the expressions. For example, here, so don't forget that e to the e is going to be a constant, right? Because e is a constant and e is a constant. So what you're doing is sort of like this. We know that 2 x is a function, but if you have 2 to the 2, that actually is 4. So that gives you an actual number. So that's the same thing. This is a constant. And when you take the derivative of a constant, we know that it's going to be, the derivative is going to be 0. All right, so what about this one? Well, in this case here, the variable is the variable is the x, right? And the variable is the base. And so here we have to use power rule, right? Which, remember, is you bring down the power, and then you subtract 1. And then over here, for part B, here is where we have the variable being the exponent, right? So in this case, this is an exponential. This is an exponential. So what do we do with this? It's going to be itself. Now, what about this one where you have actually both x be a base and x be an exponent? So how do we do the antiderivative for that? Actually, that's interesting, because what we're going to do is we're going to be more creative and use a very common technique that we have used before. This is called implicit differentiation, right? So if I have this, right? If I have this, the one of the issues that we have with this is, what are we going to do with that power, right? Who is the power? Who is the base, right? Is sort of how we're going to deal with this. Which rule are we going to be using? Well, there's a way where we can sort of minimize that confusion. What we're going to do is we're going to take the natural log on both sides of the equation, so we can bring down the power down, and now it removes that confusion of which one is which. So what we're going to do is we're going to take the natural log on the left. We're going to do the same on the right to maintain the same value of the equation. We're going to bring down the x, right? So now x is times the natural log of x. There's no longer any power. So now what we're going to do is we're going to take the derivative of the left side. The derivative of the left side is 1, or I can just say like this, right? We're going to have to use product rule for the right side. The derivative of the left side is going to be 1 over the inside times the derivative of the inside, which is y prime over y. The derivative for this, using product rule, will be derivative of this will be 1, keep the same one, plus x times the derivative of this one, which is 1 over x. Those will cancel each other out, giving you 1. And therefore, now we have natural log of x plus 1. But if you notice, we're trying to find y prime, so we're going to have to multiply both sides by y. So I did, right? I multiply the right side by y. If you guys want to see it, it's sort of like this. Multiply this by y, multiply this by y. Those cancel each other out. And now we have y times this whole thing. And then now I can replace y with whatever y was, which is originally x to the x. And so I have that y prime is x to the x times natural log of x plus 1. And there you go, right? So it's kind of cool, very creative way to actually do it. Find the derivative of that. And I hope you guys are able to now sort of recognize when this will be easier to use. I hope that you guys are able to sort of mimic this rule later on as well. I sort of kind of expect you guys to become familiar with this rule and be able to apply it. In some cases, there's examples in the homework where I encourage you guys to do that. All right, so moving on, we're gonna talk about some applications of exponential functions. One of the main ones is when we're talking about annual interest, and we've seen these rules before. But what we're gonna do is we're gonna make a connection with the exponential function. So the continuous versus the non-continuous, and an amount of $P is deposited in an account at an annual interest rate R in decimal form. What is the balance in the account at the end of 1 year? The answer depends on the number of times and the interest is compounded according to the formula. So this all depends whether the account is compounded semi-annually, monthly, weekly, daily. And so we already have this sort of formula, right? P times 1 plus R over N to the power of N times T, right? T would have been here, but since T is 1 year, it's always going to be just 1, right? So we notice that this answer is going to depend, obviously, on your initial investment and your rate. But let's remove those out of the equation by putting 1,000 and putting 8% of interest. And then we're gonna sort of make an adjustment on the how many times this is compounded per year. So what we're gonna do here is we're gonna let n be 1, 2, 4, 12. So this is compounded annually, compounded semi-annually, compounded quarterly, compounded monthly, and compounded daily. So we see how how much money we're gonna have in the account at the end of the year when it's compounded yearly versus semi-annually versus quarterly versus monthly versus daily. And so what we're gonna have here is we're gonna notice, well, what happens if we have compounded continuously? Well, that would be the case where where n becomes goes to infinity, right? So this we're gonna be able, we can actually adjust this expression and sort of manipulate it so we can actually see it this way. And what we end up having is that this will actually approach e. What we're saying here is that and this is the way we can manipulate it. So there's a rule that says that x plus 1 over x to the power of x equals e, or 1 plus 1 over x to the power of x as x goes to infinity equals e. So let's see if we have that here. So p times 1 plus r over n to the n. We're going to factor the p because p does not matter here. What we're going to do is we're going to, we need for this to become x, right? We're gonna have this become an x, this become an x as x goes to infinity. So we're gonna sort of remove this r and make it a 1 over, we need this to be a 1, so we're gonna sort of manipulate this so that we can have n over r. That will give us back this, but we want it to be n over r. So that means that this needs to be n over r, but we don't have an r, so we're gonna have to like multiply by r. That way that compensates for that. So, and then we can push the limit inside, and then now we can apply this here. Well, we know that this is going to be e, as we notice on top, and so we still have the power, so it'll be e to the power of r. And so we have p times e to the power of r. So that's sort of kind of like a way you guys can kind of think about how this is going to be how can you develop the continuous compounded function. So it just comes from the same formula. It's just um, it's just being assumed that we are approaching um, when n is becoming infinitely compounded, right? If you can think about that, like you have compounded the account infinitely in 1 year, which really doesn't make sense, right, in theory, but it means that it's continuously being compounded. All right, so, and we notice that when you apply that, then you end up getting $1,083.29, which is not so much, not so far away from what you had here. It's not a big difference, but over time it makes some difference. So that summarizes the two types of accounts that we discussed, right? If P is the initial amount deposited, T is the number of years, A is the balance after T years, R is the annual interest rate in decimal form, and then is the number of compounded years. Then we have compounded n times per year will give us this formula, and the compounded continuously will give us this formula. And we're going to compare both of them in this example. We're going to say, okay, if we deposit $2,500 is made in an account that pays an annual interest at 5%, find the balance in the account at the end of 5 years if the interest is compounded, first quarterly, then monthly, and then continuously, right? So in the first case, let's see what happens when you compound it quarterly. So this is the initial amount that we plug in. The rate is 5%. We got to put it in decimal form. Remember that. It's quarterly compounded, so that n is going to be 4. Remember that quarterly means how many times happens in a year. So there's 4 quarters in a year. So n equals 4. And then 4 times number of years, which is 5. When you put this in the calculator, this will give us $3,205.09. And we want to do this monthly, then it's the same setup, except the n is going to be 12. Remember, the monthly, you ask yourself how many times that this period happens in a year, it happens 12 times. So that means n is 12. And then you put in their account, and that gives you 3,208.40 cents. And then if you do continuously, that means you're going to use the second formula, which is P times E to the RT, where P is 2,500, R is 0.05, and then T is 5. And then you put this in the calculator, and this gives you $3,210.06. So there's about $10 of difference in 1 year. I mean 5 years, right, from here to here. But I want to make sure that we understand the difference between those three formulas, right? And pretty much the way I sort of deal with these problems is by looking at the word compounded. As soon as I read the word compounded, then I know that I'm thinking about one of these two formulas. Now, if it says compounded and it gives me a number, quarterly, monthly, then I know I have to use this one because this one depends on n. Now, notice that continuously does not depend on n. So that one does not, you don't need to deal with n because n is infinity. And we already know that that's sort of already absorbed into the exponential. All right, so a lot of the work that we did here is review from college algebra. So I hope you guys find this helpful. I want you guys to make sure that you guys are beyond comfortable with exponentials and logarithms at this moment, right? You guys already discussed this in college algebra, and I hope that you guys are now better with your explanations and logarithms. So having trouble with that will obviously will have impede you to get the right answer, and a lot of times when we are dealing with that, or be able to make the derivative much easier to do. Obviously, the derivatives of the exponentials and the logarithms are going to be important. So I expect you guys to be able to be familiar with those. And practice. Make sure you guys read the lectures and watch the videos if you guys need to, as many times as you need. Don't forget to review your material to make sure that you guys are continuously reviewing old material because, as you guys see, is being cumulative. All right. Let me know if you have any questions. I hope you guys find this helpful. I'll see you guys next time.